So in the last lecture, we have discussed about the steady state operation of the basic second order DC-DC converters in continuous time domain, that is for buck converter, boost converter and buck boost converter. We have derived the waveforms, the steady state waveforms of all the states and all the parameters of the converters. Then using volt second balance, we have derived the output to input voltage steady state transfer ratio by ignoring all the non-idealities. Non-idealities include the equivalent series resistance ESR for the inductor, for the capacitor, then on-state drop resistance and the on-state voltage drop given by the diode, and also the source voltage resistance. And also we have using the amp second balance or the current second balance, we have derived the relation between the input and output average currents for all the three converters. So in this lecture we will see the parameter design or the selection of parameters for these converters. So based on the analysis presented in the last lectures, I have drawn here a table where you can see that the name of the converter is written, and the DC transfer function of input output voltage and output input current is given, which is same V0 by Vin equals to I load by In, which means that input power equals to output power in this case. Because we have ignored all the non-idealities, so that's why the losses are zero. So the transfer function for the output voltage to input voltage is equals to that for I load to In. And I have also written, so based on the analysis done in the last classes, the preferred range of operation, I'll write here preferred range of operation for a buck converter is you run a buck converter for high duty ratios, that is say almost around 0.75 to 1, and for boost converters you operate it at the low duty ratios 0 to 0.4, and buck boost converters you operate at medium duty ratio, that is from 0.3 to 0.7. So here you can see that for the buck boost converter you can get a wide range of operation of the duty cycle. So D is 0.3 to 0.7, means if D is from 0.3 to 0.5, then it acts as a buck converter, and from 0.5 to 0.7 it acts as a boost converter. So today we will derive the relation of the parameters of these converters with respect to the system parameter or the control parameters like duty ratio. And the parameter of DC-DC converter includes the value of the inductance, the value of capacitance, peak ripple of the inductor, that is delta IL, the peak ripple of the peak to peak, you should say, the peak to peak ripple of the inductor current delta L, and same ripple for the output voltage. We derive a relation of these all parameters with respect to the control parameter D. So here D is the control parameter, because for load regulation, as the load changes momentarily, the output capacitor supplies power to the load, so its voltage decreases. Then some control action has to be done on the duty ratio, and the duty ratio has to be adjusted. So this is assuming that Vin is constant. So for a constant Vin, we have to increase the D or decrease the D for the V0 to stabilize to its previous value for a load change. And if load is same and the input voltage changes, similarly you have to adjust the duty ratio. So here D is the control variable. So we'll derive all the converter parameters in terms of the control parameters, which is the steady state duty ratio D. So we'll take first buck converter. So inductor. So how to remember the circuit diagram of a buck converter is, you should remember that the output side there is a LC filter. This is a LC filter. There is a voltage filter sitting at the output side. Okay, so we'll see the volt second balance of an inductor. We know that VL is L DIL by dt. You can write it as L delta I by delta T. You can write it as L into delta I, means instead of writing like this, you can write as VL during on time is equals to L. So delta I will remain same by delta T on, and this equals to V of when T equals to T on and when T equals to T off, or when S1 is off, S1 is on. S1 is 1, S1 is 0 is L delta I by delta T off, because this is the nature of the inductor current. This is delta IL, this is T on, this is T off, and this whole is T switching. So delta will be same. So it can be written as V. If we substitute, what will be the VN on when the switch is on? When the switch is on, the voltage across inductor is V in minus V naught, where V naught is less than V in. So it is V in minus V naught equals to L into, let's write it as delta IL by delta T on. What is the value of the time delta T for on time? It is D into T switching. So I'll write D into T switching. If I write in terms of switching frequency, then F switching is 1 by D switching. So it goes to the numerator, F switching. Similarly, this is for T on. For T off, when the switch is off, the voltage across inductor is minus V naught. So it will be minus V naught equals to L delta IL by delta T is 1 minus D into TS, or 1 minus D by F switching when T equals to T off, like this. So we can use any of this relation, either first one or second one, to derive the relation between L and delta L. So you can write, considering, I'll take the off time, T equals to T off, let me consider T equals to T on. So what it will be? It will be V in minus V naught equals to L delta IL into F switching by capital D, or I can write as L equals to V in minus V naught into D by delta IL into F switching. So in this case, I have derived the value of the inductance in terms of the input output voltages, the steady state duty ratio, the peak to peak inductor current ripple, and the switching frequency. Similarly, if I use the amp second balance for the capacitor, you know that this is T, this is IC. From here, if from here to here it is T switching, then you know by geometry this is T switching by 2. This part is T switching by 2. This is A3, this is A4. This whole is delta IL. Okay, this whole is delta IL. So what is this? This will be delta IL by 2, because the same inductor current waveform is pushed down so that its average value is 0. That's why it is exactly pushed by half of the amount. So exactly half portion will go above the T equals to 0 axis and half will go below it. So that's why it is T switching by 2. So you know that Q equals to C into V. So if we differentiate this equation with respect to time, so dq by dt is C into dV by dt. So the rate of change of charge, you can write it as capacitor current equals to C into dV by dt. This you can, or what you can write is IC is dq by dt. So you can write Q as integral IC into dt plus Q naught. So Q naught is the initial charge at the capacitor. Let's assume that initially the capacitor is discharged. So Q is integral IC dt. So it is the area under IC versus time graph. So it is either A3 or A4, because A3 equals to A4. So the area we can, either of the area we have considered. So similarly for Ward cycle balance, we are considering one of the equation of the two here, where T is T on or T is T off. So similarly for capacitor, you have to take any one relation. So what you can write is Q equals to, therefore Q equals to A3 or A4. That's why if you write here, area of a triangle is half into base, that is T switching by 2. We'll replace T switching as 1 by F switching. So 1 by 2 F switching, because it is T switching by 2. Half into base into height into delta IL by 2 equals to C into V, equals to C into V. So therefore, if you derive C, it is delta IL by 2 to the 4 to the 8 F switching into V. This is the value of capacitance. So what we observe is that the inductance and the capacitors, the inductor and the capacitor are a function of switching frequency. Both are inverse relation of switching frequency. As the switching frequency increases, the size of the required size of the inductance and capacitor reduces. So L is a function of duty ratio also, but C is not a function of duty ratio. It is only a function of output voltage and the peak to peak inductor current ripple. So this the approximation we did for the volt second balance, that is VL is L, di by dt is L delta by delta t, where we replace delta t by t on or t off. So the similar type of analysis we have to do for the capacitor for finding the capacitance. So what we'll do is Q equals to CV, and dq by dt is C into, let's write delta V naught by delta T. Delta V naught by delta T. So we have derived the inductance and the capacitance as a function of the plant parameters. Now let us derive some more relations. So P in equals to P naught, that is no non-idealities. So what is P in? It is V in into I in. Average values we have to write equals to V naught into I naught. This we know. Output we can write as V naught into I naught. I naught is V naught by R. So it is V naught square by R. This is V naught square by R equals to P in into V in. Now we'll see if we can write the value of inductance and capacitance as a function of only the plant parameters by ignoring delta I and delta V. Now for buck converter, we have found these relations of L and C as a function of D and the plant parameters. Let's find for boost converter. So we don't need to redraw all the waveforms, we just have to draw the circuit diagram. So the boost converter is that the inductor should be placed at the input side and the switch should be in the middle leg, parallel leg. So if we write VL is L dIL by dt, this you can write as VL on is L delta IL by T on directly, or VL off equals to L delta IL by T off. This can be written as, when the switch is on, VL on equals to V in is L delta IL by D by F switching. Similarly, what is VL off is we can write V naught minus V in equals to minus L delta IL by 1 minus D into F switching. Why I have written minus on the right hand side is because the voltage across the inductor during off state is V in minus V naught, but in boost converter V naught is greater than V in, so we have to write everything in terms of positive, so that's why minus sign comes. So considering T equals to T on, V in equals to L delta IL F switching by D, so therefore L we can find as V in D by delta IL into F switching. In the buck converter it is D into V in minus V naught by delta IL into F switching. In boost converter it is only V in D by delta IL F switching. So let's say if the power rating is same and the voltage ratings are same, if the converters are operating for the same duty ratio, the buck converter will have lesser inductance requirement. Why? Because the inductor is placed at the output side and the average value of the inductor current will be equal to the load current, and the output current is continuous. But in the boost converter, the inductor is placed at the input side. Then the DC transfer function between output and input current, the relation is 1 by 1 minus D. That is, I in by I out is 1 by 1 minus D. So V naught by, whatever is the relation of V naught by V in for any converter, V naught by V in same is the relation for I in by I naught in this average values. In this case, I in is IL and I out is I load. So IL by I load is 1 by 1 minus D. So the same relation will hold here. Similarly, using the amp second balance, Q is CV. So we can write as integral IC dt equals to C into V. This is area of IC versus time graph. In this case, what we have to do is, this is ID current, ID1, this is diode D1, this is IC, and this is I load. Out of ID1 current, ripple goes to IC and the remaining load goes to this, and ID is equals to IL when the switch is off. That is, the average value of ID is 1 minus D times of IL. This we can write ID1 equals to 1 minus D times IL. This is the average value of the current. This goes to the load, so that equals to the load. This statement is also verified using the amp second balance, which we have already derived. So the nature of ID will be the off time, but the only thing is that the waveform is shifted down. By what value? The waveform is shifted down by V naught by R value. So this is A3 and this is A4. So either A3 or A4. A3 equals to A4. So we'll take the one which is easy to calculate. So we'll select A4 because it's simple rectangle. So therefore it is length into breadth. So D into T switching or D by F switching into the load current, that is V naught by R, equals to C into V naught. Actually, what I forgot to write is here is V as delta V naught. This should be delta V naught. So delta V naught. Here it should be delta V naught, because delta Q is C into delta V, and integral of delta Q is the area. So that's why similarly here delta Q equals to C into delta V, that is C into delta V naught. So it will be delta V naught. Time is d into t switching, or d by switching into load, that is V naught by R equals to C into delta V naught. So we can find C. C is what? D into V naught divided by R into F switching into delta V naught. This is the value of capacitors and inductance for a boost converter in terms of the plant parameters: V in, D, F switching, V naught, and the ripple values of the inductor current delta L, and the ripple of the output voltage delta V naught. For buck and boost converter we have derived. Lastly, we'll derive for buck boost. For buck boost, again we'll draw the circuit diagram. So the input side of the buck boost converter is similar to a boost converter. Here there should be a switch, then an inductor, then a diode, then a reverse polarity of a capacitor, and a load. So V naught is like this, plus minus, and V in is reverse polarity. This is S1, this is D1, this is L, this is C. So instead of writing these two cases, I'll directly write which one is easy to write. So when switch is on, voltage across inductor VL is V in. So I'll directly write VL on equals to L delta IL by T on, that is D by F switching. So VL on is V in. V in equals to L delta IL F switching by D. So therefore L is what? V in D by delta IL into F switching for a buck boost converter. And so again, this is ID, this is IC, and this is iLoad. IC is what? ID minus iLoad, because ID equals to IC plus iLoad. So the same relation holds for the boost converter also. So I'll directly copy paste the C expression, that is D into V naught by R into F switching into delta V naught. So the same relation for capacitor holds, because the same waveform of the diode current which you already saw here, this waveform is valid for the buck boost converter also. Only the thing is that the currents have reversed their directions, but the KCL still holds. That is for boost converter, ID1 equals to IC plus iLoad. Here also ID1 equals to IC plus iLoad. So the same expression for capacitor will hold true instead of solving it. And also you can see that the output of a boost and buck boost converter looks similar. That's why the capacitance value should be, the expression of the capacitance value should be similar. So for all these three converters we have derived the plant parameters. So we have known how to find the value of L and C in terms of the ripples. Now this is how we should select L and C, so in terms of the ripple. But for designing the inductance and capacitance, you cannot get the exact value of the L and C which you found from these expressions. There might be some deviations from the values of the L and C which you get in the market. So now what we assume is that, assume L, C are known. So first you saw what is the type of the converter, let's say boost converter. These are the expression for L and C. So you get some value of the inductance, you get some value of capacitance. Now you went to market and purchase the inductance and capacitance. So now L and C are fixed. Now L and C are fixed. Now you find delta IL and delta V naught in terms of the plant parameters. So what you will do is, it is very simple. In the expression of L, just again solve this expression of the L in terms of delta IL. So what will be delta IL? It will be V in minus V naught D. Delta IL will be V in minus V naught into D, V in minus V naught into D by L into F switching, divided by L into F switching. So we can again rewrite this expression because we know that V naught equals to D into V in. So we let everything in terms of V in. So if we substitute, it will be delta IL equals to V in minus dV in divided by D by L into F switching. So therefore delta IL will be, if we take V in common, so V in into D into 1 minus D by L into F switching. This is the expression for the ripple which you can find, the maximum peak to peak ripple which you can find for a which converter? For a buck converter. So delta L is a function of input voltage, the duty ratio, the inductance and the switching frequency. So now we cannot write again V naught. So this expression you can write in terms of V naught, or you can write in terms of V in. I have chosen to write in terms of V in, so it is V in into D into 1 minus D by L into F switching. We assume that L and C are known, we are selected, switching frequency is constant. As I have explained you in the previous lectures, that we are going to apply pulse width modulation, which is comparing a constant signal, modulating signal, with a high switching frequency carrier signal. The carrier signal can be sawtooth or it can be triangular signal with a switching frequency of F switching. So the switching frequency is fixed. It is a constant switching frequency PWM scheme, control scheme. Where you can control it in open loop or closed loop, that doesn't matter, but it's a PWM scheme. So FSW is fixed. So this is known to you. So now if we derive the expression of delta V naught, so we can write delta V naught as delta IL by C. Similarly, delta V naught equals to, what was it? Delta IL by 8 F switching C. Delta IL by 8 F switching into C. Delta V naught is delta IL by 8 C F switching. Yes, and delta V naught we can substitute from here. So therefore delta V naught is 1 by 8 C F switching into V in into D into 1 minus D divided by L into F switching. So therefore delta V naught will be, nothing is cancelled and nothing can be further simplified. So it is 8 L C F switching square. This is for the buck converter. So now let's plot D say that we have two y-axis, delta IL and delta V naught, and a common axis, x-axis, that is D. So here d is 0, here d is 1. Again 0.5, 1.5 means 0.75, and here it is 0.25. So let V in by F switching is some A. Therefore delta IL, say it is y1, y-axis, it becomes yn equals to A into d into 1 minus d. Say d is 0, so it is 0. Say d is 0.25. So we'll keep on substituting. I'll write a table. This is delta IL value, this is delta V naught value, where the constant V in by L into F switching is A, and V in by 8 LC F switching square equal to some B. So instead of doing this thing, I'll directly write here that y1 is A into d into 1 minus d, and y2 is again b into d into 1 minus d. So I'll paste it here. And okay, here I'll write d. Say it is 0, 0.25, 0.5, 0.75 and 1. So if d is 0, delta V is 0. Similarly it is 0. If d is 1 by 4, so it is 1 by 4 into 1 minus 1 by 4. So 1 by 4 into 3 by 4, that is 3 by 16. So it is 3 by 16a. If it is 0.5, so 1 by 2. 1 by 2 into 1 minus 1 by 2 is 1 by 2. So it is 1 by 2 to the 4, a by 4. If it is 0.75, that which you can call as 3 by 4. 3 by 4 into 1 by 4 is again 3a by 16. Similarly, replace a by b. So 3 by 16 is less than a by 4. So it is like this. Say this is 3a by 16. This is a by 4. And again it is 3a by 16. It is like this. And okay, I'll use some other color. So this is delta V naught, and this y1 axis is delta IL. So what you observe is that the ripple as d tends to 0, delta IL and delta V naught tends to 0. But this is practically not possible. Impossible. Which is practically impossible. So you should have some let's say some minimum duty ratio 0.001. So t starting from that. So at high as the duty ratio increases from 0 to 0.5, it increases in a non-linear fashion. It increases in a non-linear fashion. So if you want lesser delta IL and delta V naught, So 0.01 is less than t is less than say 0.25, and d has to be more than 0.75. 0.75 is less than d is less than 1, or say 0.99, because 1 is practically not possible. These are the range of operation of the buck converter. For the buck converter, so as d is 1, again it is 0 0. So as d tends to 0 and d tends to 1, for both of these cases it is 0. So we have two sets of ranges of operation. This is region 1 and this is region 1 and this is region 2. So which region to select, where to operate the converter? Now we know that L, what was L for the buck converter? V in minus V naught D. So it is V in minus V naught into D by F switching into delta IL. So even you can further simplify this equation. So we can write V naught is D into V in. So you can further simplify V naught as D V in. So again it will be V in into D into 1 minus D divided by delta IL into F switching. So let's for the boost converter, no need to rewrite because there is no V naught term, and similarly for buck boost converter there is no need to rewrite, which is V in into D into 1 minus D by F switching into delta IL. So what happens at the region 1 is that the peak current rating of the inductor, the rating of the components like L and C, what was C? Delta IL, eight F switching delta V naught. Delta V naught. Yes. So what happens is this delta IL, and here we have delta V naught by delta IL. So it is some constant K by delta IL, and it is again some constant K1, this is K2 into delta IL by delta V naught. So what happens is in the region 1, both delta IL and delta V1 in region 1, delta IN and delta V naught are less. So therefore L will be high and C will be smaller. So smaller term divided by smaller term is a smaller term. C will be reduced. Even for R2 region, the same case, the same condition holds. In R2 and in R1 and L2, the same condition holds. Now if you want to reduce the inductance and see how should we select the capacitor for the rate of change of delta IL by delta V naught. So we have to establish relation between delta IL and delta V naught. So it is observed that in R2, L and C are optimized. And also delta V naught, delta IL are less. So what we have to do is for optimizing L and so for both R1 and R2 cases, L will be high because delta L is less. So we want delta V naught, delta IL ripple to be less. We also want the component to be lighter component. So if L is less, then what happens is the inductor will not be bulky. The inductor is a function of the switching frequency. So as switching, given that the switching frequency is constant and you want to reduce the size of the inductor, then the peak current rating of the inductor should be reduced. So for a lighter IL, peak should be reduced. What is IL peak? IL peak is delta IL by 2 plus capital IL or I load, and for a buck converter, I load equals to IL. So this you can write as delta IL by 2 plus I load. So here it's a function of I load. So I know I load is not in your control. In your control is only delta IL term, uncontrolled. This you can write as uncontrolled. This is under your control. So delta IL is a function of many terms. Delta IL is a function of input voltage, duty ratio, and L by switching. Given that V in L F switching are they are constant or they are fixed, IL is only a function of D into 1 minus D. That is where we have to see only the region in which it operates. And if by assuming that there are no non-idealities, so we can say that there is no relation between I load and D. There is no direct relation between I load and D. So to reduce the I peak current, R2 is preferred. R2 is preferred, where L and C both components are optimized. Also delta L and delta V load are reduced irrespective of the load. That's why in the last lectures I have told you that for a buck converter, R2 or the higher duty ratio region is preferred. Now very quickly we'll see what is for a boost converter. So for a boost converter, delta IL we can write as V in D by L F switching. V in D by L into F switching, which was delta IL, and delta V naught was D V naught by RCF switching. D V naught by RCF switching. So it is A into D. Y1 is A into D and Y2 is B into D. So it's a simple linear combination. So what you can write here is, very quickly I will draw delta IL, which is Y1, and here I will draw the slope. Here for A is V in by L F switching, and B is V naught by RCF switching. So here I am not bothered that A is greater than B or B is greater than A. Here I am just getting the relation like this. So this is delta V naught, 0 to this is from 0 to T. Sorry, not T, 0 to 1. So for smaller, delta IL and delta V naught, small range of D is selected. So that's why for a boost converter, this range is used. Say 0.4, this is the preferred range of operation. Again, IL max or IL peak will be delta IL plus I load. Sorry, delta IL plus capital IL. And in the boost converter, where is the boost converter? In the boost converter, this you can write as 1 by 1 minus capital T. IL is not equals to I load or I naught. So IN is IL. So IL is I load by 1 minus T. This you can write as delta IL plus capital IL, which you can write as, where is it? Here. I load by 1 minus T. So again, delta IL you can write as V in T by L into F switching, plus here you can write as I load by 1 minus T, which is IL max. So this is the expression of IL max for the inductor. To reduce the size of the inductor, we have to optimize this IL max to a smaller value. So I load is not in your control, so only D is in your control. So I load by 1 minus D term is again this is a straight line. This is a parabola or quadratic. This I can write as quadratic. So only this term you can control. So if D is less, then only IL max is less. That's why. So a boost converter is operated preferably. It's not like you cannot operate, but it is preferable if you operate at lower D ratios. At lower D, typically 0 is less than T is less than 0.4, around this range. Lastly, we'll see for a buck boost converter. This is very easy to analyze. For a buck boost converter, quickly we'll write delta L and delta T. Delta L is V in D by LF switching. This is delta L, and delta V naught was, I think, same for a boost converter. dV naught by RCF switching. dV naught by RC into F switching. Again, the same graph I'll draw. Or okay, where A is again V in by LF switching and B is V naught by RCF switching. So it's again it is a linear combination of D. So it should be operated at lower DT ratio. But the twist is here in the IL peak. That is, IL max is delta IL. Oh, sorry, it is delta IL by 2. Delta IL by 2. I forgot to write here. Delta IL by 2. So IL max for buck converter, I forgot to write here the expression. V into D into 1 minus T by 2 LCF switching square plus I load for a buck converter. Now for a buck converter, I load equals to IL. So I'll directly write this was IL. So it is I load. This is IL max for the buck converter. This is IL max for the boost converter, and this is IL max for the buck boost converter plus IL. So V0 by V in, we'll write mod of V0 by V in is mod of I in by I0. What is that? D by 1 minus T. So in a buck boost, the inductor is placed at the middle leg. So we have to derive the relation of the inductor, average value of the inductor current, which we'll see in the waveform. So buck boost is here. So here what happens is, this is IL, this is ID1, and this is IS1. When the switch is on, IS1 equals to IL. When the switch is off and the diode is on, ID1 equals to IL. Okay, and so that's why IS1 is what? D into IL, and ID1 is 1 minus D times of IL. So IS1 is IN, which is D into IL, and ID1 is what? That is the load current, which is 1 minus D times of IL. So therefore IN by ILOD, which is IN by I0, is D by 1 minus D. So this you can easily write. We'll write in terms of ILOD only. So therefore IL for a buck boost converter is ILOD by 1 minus D. Easily we have found out, and we substitute it here. So this we can ILOD. Or no need to write this, no need to do this derivation. We can directly substitute here. So delta IL by 2 plus capital IL for a buck boost converter. Where I have written? Here, buck boost. So let's assume that this section ends here. Capital I is ILOD by 1 minus D. So ILOD by 1 minus D. So therefore IL max will be V in D by 2 LF switching plus ILOD by 1 minus T. You can also write ILOD as V0 by R, or D into V in by 1 minus D into R. If you write this, then what happens is, therefore IL max now becomes V in D by 2L F switching plus D into V in by R into 1 minus D whole square. This is the ultimate expression for the buck boost converter. So for a buck boost converter, what happens is that the requirement for delta IL and delta V0 says that operate at less duty ratio, but ILOD is not in your control, but this term, both the terms are in the control, are in the control, that is D should be optimized. D should be optimized as it is. So this is IL max is what? A into D plus, say it is some C into D by 1 minus D whole square, where C is V in by R. So it has a quadratic term, so which is very high at low and high duty ratio. So this term has very high value at low and high duty ratios. So that's why we select mid-range. Mid-range of D, that is what we have selected here, 0.3 to 0.7. Say around 0.3 to 0.7 for a buck boost converter. So as I explained to you in the previous classes that what should be the range of operation of the buck boost converter, I had just orally said ki for buck it is high frequency range, for boost it is it is high duty ratio range, for boost it is low duty ratio range, and buck boost it is mid range. But why it is so, that I have derived in today's class. So as to conclude today's class, we'll just write a comparison table. So comparison table, what we'll write is the expression of L C. Okay, first is the converter, then I have to write the expression of L C delta. So delta IL you can get from the expression of L only, so that's why I'm not writing it separately. Or let us write in terms of delta IL and delta V naught. Delta IL, delta V naught, and the final is IL max or IL min. Typically we consider IL max for designing the inductance values. That's why I have written like this: buck boost and buck boost. So now let me write where we ended. We have to write in the optimized form, not in this form. So yeah, boost, no, boost. It should be buck. This should be buck. Buck. Then boost, yes, and then buck boost, then boost. Then first we write buck boost and buck boost. Yeah. So we'll write V in D into 1 minus D by L F switching. V in into D into 1 minus D by L into F switching, and delta V naught for buck, v in d into 1 minus d by LC f square. LC f square, same numerator, v into d into 1 minus d. Then the expression for IL max for a buck converter will not write in terms of I load. We'll substitute I load in terms of, so here we'll write I load as V naught by R, which is D into V in by R. Simple. So V in D into 1 minus D by 2 LCF square, V in into D into 1 minus D by 2 what? 2 LCF square plus d V in by R. For boost converter, V in D by LF switching. And delta V naught is d V naught by RCF switching. I hope it is correct. d V naught by RCF switching. And for boost converter, the value of IL max is V in D by 2 LF switching, V in D by 2 LF switching plus, we'll let the plus small, plus boost. Here we can write I load as V naught by R, which is V in by 1 minus T R. So for all the three converters, we can write I load as V naught by R. Then separately we have to write for each converter what is the relation between V naught and V in terms of D. So for boost converter, it is V naught is V in by 1 minus D. So it is V in by 1 minus dr. So I load by 1 minus d is what? V in by 1 minus d square r. V in by 1 minus d whole square r. For buck boost V in d by LX switching. This as it is for d V naught by RCF switching. Again same. And the expression for is this. So here it is this expression as it is plus d V in by R. So d V in by 1 minus t whole square into R. This is the comparison table for the different converters. Okay, we derive, so range of operation is I think we have already written in this first table. Yeah, in this table this is a converter and the preferred range of operation. So if we write mod of V naught by V in, then this minus sign will vanish. So in today's lecture, what we have done is we have designed the parameter of these DC converters. First L and C in terms of the ripple and the plant parameters. Then again we have rederived the, by assuming that we have already selected L and C and other components, we have rederived the expression of ripple content in current, inductor current, and the capacitor voltage or the output voltage in terms of LC and duty ratio. And we have also considered the peak inductor current for seeing the range of operation of the particular converter, the range of the duty ratio for which the converter should operate. And we found that for buck it is higher duty ratio range, for boost it is lower duty ratio range, and for buck boost it is middle range, where in middle range it is from 0.3 to 0.5 it can operate in buck mode, and from 0.5 to 0.7 it can operate in the boost mode. So buck boost converter, it operates in mid duty ratio range in buck as well as boost mode. It is preferable mode, it's not like you have to operate, it is preferable because you will get so there are things like you have to reduce the ripple in inductor current and output voltage, simultaneously you have to reduce the peak current. So you have to find a range of duty such a way that all the three things are optimized. So that we saw in this lecture. In the next lecture we see the discontinuous mode of operation and the analysis of these three converters in the discontinuous mode, starting with critical inductance calculation. Thank you.